Hello everybody, time for another video on a new topic. So in this video, which will probably have a part 2 coming up, I'll give you an introduction to something called u-substitution. U-substitution is a method to evaluate indefinite integrals, okay? As far as what an indefinite integral is, I posted some videos already to introduce that concept, but another way to think about it is to call it an antiderivative. Math and most subjects are full of new vocabulary words and so on, and so indefinite integral is one of them. Think of it as an antiderivative if you want to. Now, we have a rule for indefinite integrals that are like this. If you want to find the indefinite integral or the antiderivative of x raised to some power n, that power n can be anything except -1, then here's your rule to evaluate that and find the antiderivative, okay? Now, you can apply this to any problem that looks this way. So for example, you see this one right here, this antiderivative, this indefinite integral. You could read this as, what's the antiderivative of r to the 4th power? R is the variable here. Well, it's a different variable. I wrote the rule with x, but you can change what the variable is if you want to. The variable can be r if you want to, but the rule does apply, okay? It's the variable to some power, and then that power is not -1. So if we apply that rule, we add 1 to the power, and we divide by whatever number we get. In this case, that's 5. And our antiderivative is r to the 5th power over 5 plus c. Now remember that this is the antiderivative, okay? What I'm saying is if you take the derivative with respect to whatever the variable is of this, and the variable is r, okay, then if that's right, you'll get r to the 4th power, okay? And if you use the rules of derivatives appropriately, you can check this and show that you do in fact get r to the 4th power, okay? If you took the derivative of this with respect to r, you would bring this power down to the front. You'd have 5 over 5 in that case. The 5s would cancel. You would subtract 1 from this, okay, and you get 4. And then what about the plus? Well, you'd carry the plus. And then what's the derivative of this thing? See that capital C there? What's the derivative of that? Well, capital C is the constant of integration. It is some unspecified constant. And the derivative of any constant, anytime, anywhere, is 0. All right, so check. We got r to the 4th power. All right, so that's a little bit of a segue. Not segue, that's not the right word. Tangent, I don't know. But yes, you can check your answer in this thing no matter what the rule is, serves as the antiderivative. Now, I can apply this to any problem that looks that way. What about this one? 1 over t to the 3rd power dt. T is the variable here. Well, that doesn't really look like the rule applies, but with the laws of exponent, I could write this as not 1 over t to the 3rd power, but t to the -3 power. And then this rule would apply. I use the rule and I simplify to get that. So we have a rule for any problem that looks this way. We don't have a rule for something like this, okay? Like even if you were to rewrite this and say you really wanted to use this rule where it says your variable to some power n, as long as that power is not -1, then you might say, well, I could write this as 3m minus 1, and instead of writing 1 over that to the 4th power, I'll write to the -4 power. But that the rule just doesn't apply to this. That is more complicated than this rule allows. It says that if you have a variable, whatever your variable is, to some power n, such as r to the 4th power, or t to the minus 3 power. It does not allow for anything more complicated than that. Okay, so we don't have a rule for this, but in this video, I'm going to show you how we can address it. I'm going to show you a rule, a way to do it, okay? But for now, we need to recognize what we're able to do and what we're not yet able to do, okay? I think that'd be a good place to start with the video. Okay, all right, so we don't have a way to do this one. So if I'm going to do this problem, okay, then the method we use is called u-substitution. All right, and I want you to think about that word a little bit. Substitution. By that word, by the word substitution, what we mean is that we're going to substitute the original variable in a way that the integral becomes so simple that our original rule would apply to it. Because the reason why this rule does not apply to this problem is because it is too complicated. It has more stuff in it, to put it bluntly, than this rule allows for, right? This does not say, okay, the variable's m here. It does not say m to the minus 4 power. It is more complicated. It is 3m minus 1. So substitution, the method I'm going to show you, it just is a way that we can reduce that down and make it simpler, and then the rule would apply. Okay, so now, like anything in math, I know I can just show you how to do the substitution, but I wanted to work up to it a little bit with some preliminary information. Here are the guidelines. I'm going to show you the guidelines, but like some things in math, it is hard to learn this by just the guidelines. We're going to have to talk about the guidelines. We're going to have to look at some examples, and then maybe come back to the guidelines and do more examples, okay? It won't probably be enough just to tell you the guidelines, and it probably won't be enough just to show you the examples either. We're going to need to use both of these back and forth. Here's how it works though. So we substitute the original variable, whatever it is. In this case, the original variable is m. We're going to substitute that away. We're going to put another variable in its place. But we also have to substitute the differential. This dm, in my original video on this topic, I told you that the dx, that's called a differential. That will signify what the variable is, okay? It needs to be there, all right? But it's, for now, it's going to signify what the variable is. Dx means the variable is x. Dr means the variable is r. Dt means the variable is t. Dm means the variable is m. Okay. So we have to substitute both of those, okay? And what we do is we choose a substitution so that our problem becomes so simple that this rule becomes applicable, okay? Because so far, it is not simple enough for this rule to become applicable. So there are other ways I can give you a guideline for choosing the substitution. There are different ways, rules, and so on to address thinking about what the substitution should be, but I'm just going to tell you, because I think it'll work for what we need, that you want this problem to become simple enough so that that rule applies. That's what I'm going to say about it. Okay. And the substitution must completely eliminate the original variable. That means if the original variable is m, then our substitution must make all the m's everywhere in the indefinite integral go away. All right? Okay, so here we go. Here's how we'll do it. So if I'm going to use my rule that's like this, okay, it says if you have your variable x, let's say, to some power n dx, if I got a rule for that, okay, and then that's what the rule's ultimately going to be, then the way that I should substitute is like this. Now, we call this u-substitution because the variable that we substitute into the problem is typically chosen to be u. I guess you could choose it to be whatever you want, but the way people do it is they choose it to be u. So if this, think about it. If this is going to become like that, okay, then it would make sense that I let this be my substitution. So I'll say I'm going to introduce this variable u, and u is going to be substituted in place of 3m minus 1. You see why that would turn this problem into that one. Because what would it look like if you put in place of 3m minus 1 u? It would look like u to the minus 4 power, and then this rule would be applicable, and then we could work it. Okay, but I did say that we have to substitute the differential also. Here's how you do that. So if we have our original substitution that we choose, now this part we always choose. Okay, you choose that, you decide what that should be. And I gave you my rationale for choosing it to be this way. All right. As far as substituting the dm, the differential, we take this and we take the derivative of both sides. Now, the derivative of u is technically 1. But in order to keep track of our variables, we say 1 du because that was a u derivative. And the derivative of 3m minus 1 is 3. But we don't just say 3, we say 3 dm because that was an m derivative. But choosing this and taking the derivative of both sides of that, writing du on the left because it was a u derivative, and dm on the right if the variable's m because it was an m derivative, that is how you substitute the differential. Okay, so your substitution is going to involve both of these things. All right. Whoops, I don't, oh gosh. Please don't. Okay, here we go. That's going to have to be good enough. All right, so that's how we do it. Now look at this. Now the next step. If I were to apply my substitution in this step right here, then here's what it would look like. For 3m minus 1, I'll put u in. Okay, good. Now I need to substitute the differential. See how it says dm right there? And here this says 3dm. Notice how this doesn't perfectly substitute. And it usually won't. But these are equations. And you can do with these equations what you do in algebra with equations. You can add numbers to both sides. You can divide numbers by both sides. So in order to adapt this so that it will substitute up there, because I don't see 3dm, I just see dm. And math is very precise. Like if this does not look exactly like that up there, then I can substitute it. All right. But look, this is an equation. I'll just divide both sides by 3. So if I do that and I divide both sides by 3, then I'll get du over 3 on one side and I'll get dm on the other side. And then this I can substitute. You see, in place of the dm, I'm going to put du divided by 3. Okay. Now that completes the substitution. Okay. The goal of the substitution was to make this rule applicable, and now it is. All right, now it is. The goal also is to completely eliminate the original variable. So if the original variable is m, like that's totally got to go. And so now it's gone. The m's gone. My integral is completely in terms of u. Now, you might say, what about that like du over 3? What do we do? Well, that is a number, and it is a factor of 1/3. There are lots of rules for indefinite integrals. There's this one, which we're ultimately going to use. And then there's this one. Okay, so let's say that k is a constant. Okay, it's a fixed number, whatever it is, such as 1/3. Then for any indefinite integral, if you have a constant times your function, whatever your function is, then we can take that constant out and we can solve this indefinite integral, whatever the answer is, and then we'll multiply the answer by k. So this over 3, this is actually a 1/3. So we're going to say, well, this is 1/3 times u to the minus 4 power du. Okay? All right. And then we'll worry about the 1/3 later. We'll just work this and we'll worry about it later. Now, okay, the rule's applicable, right? It's like the variable's u, it says u to the minus 4 power. This is exactly what I wanted. I wanted this rule to be applicable. So, okay, here goes then. It's 1/3, and my rule says I need to add 1, so it's like -4 plus 1. So it's -3, and then I divide by -3, and then I do plus c. Okay, and I'll get, like, with a little bit of cleaning up, my term will be negative. I'll get a 9 on the bottom, and I'm going to say like u to the 3rd power plus c, and then times 9. So -1/9 u to the 3rd power plus c. That'll be my answer. Okay, I got my rule to become applicable to it. I got my answer. That was my objective. There's only one more thing. It would make sense that if the original problem was within the variable m, that it would be sensible, right, to give the answer in terms of that same variable. I used the variable u just to simplify it so that my rule became applicable. But I want to get my answer back in terms of the original variable. How do you think that I take my answer? So here's my answer. How do you think I can put that back in terms of the original variable m? Well, I use my substitution. Like within this problem, u is the same thing as 3m minus 1. You can substitute one for the other. Okay, so I got u right there. I want to put the original variable m back in. Okay, u is 3m minus 1. So my final answer is -1 over 9, and I'll get 3m minus 1 to the 3rd power plus c. Okay, so yes, that's what I was looking for. -1 over 9 times 3m minus 1 to the 3rd power plus c. So I got it. All right, now that's the whole procedure. Every time it's going to look something like this. We'll have to choose some substitution. We'll say u equals what? What will probably guide that substitution is wanting to use this rule. So if this thing was just simple, if this was just some variable, if this just said x or u or whatever to some power, then call that thing your u. Okay, so you'll substitute u for this, but then to substitute the differential, we take the derivative of both sides, keeping track of the variables. Okay, and then even if we have to divide the numbers out, we substitute that also. And then our rule is applied, we solve it, and then we enter back the substitution to get the original variable. Then we get our final answer. Okay, now that was really slow. I went through the details slow. It's always, if I can choose fast or slow, I'll have to choose slow for the videos, because you could always skip through them if you wanted to. But I hope that you get to see, 1, I read you the guidelines, and 2, I put them into action. I explained a little bit about how I was using these guidelines along the way. Now let's try another one. Okay, so we'll go a little bit faster. What about this one? Now, again, like I'm thinking when I see this, well, that's a complicated problem. It has more stuff in it than the problems we're used to. But I'm wondering, like, if this is applicable. Like, you know, can it be that simple? Could it just be x raised to some power? Because that's the way I need it to be, because that's the rule that I have. So let's do like this. First of all, I don't see any exponents, and if I'm gonna have any hope of using my rule, which this looks way too complicated for that rule to be applicable to it, but if I have any hope of that, I need to write everything with a power. So like, you know, this root right here, instead of writing square root, I'll write 6x to the 8th power minus 7. And then instead of a root, I'll write 1/2 like that. And so dx. Okay. All right. So there we go. Now, how do you think you could substitute? I'm going to choose substitution. I'm going to say u equals something. And that will be my substitution. I have to choose that and figure it out. Okay. How do you think that you could choose that, like choose something in here to be u, so that it becomes so simple that this rule is applicable? Well, generally, right, that's what we want. We want this to become simple. The other guideline for choosing your u is you choose it to be the part of the problem such that if you took the derivative, you would get the other part of the problem, with perhaps the constants being different. Let me show you what I mean by that. So if I choose u to be 6x to the 8th power minus 7, then this other part will be my du, because remember, I have to substitute the original variable x, but I also have to substitute the differential dx. If I do it this way, everything will fall into place with the way I need it. Let me show you. Okay, so I'm going to choose this. This will work, okay? Now for my differential dx, here's how I arrive at that substitution. I'll take the derivative of both sides of this. The derivative of u is technically 1, but we'll say 1 times du, so du. Over here, what's the derivative of 6 times x to the 8th minus 7? Well, the rules for derivatives, I bring that 8 down, I get 6 times 8, so I get 48x to the 7th power, and then the derivative of subtract 7 would be 0, so I'll just get 48x to the 7th dx, okay? Now, that x to the 7th, the other part, that's how I'm going to get my differential substituted, okay? So watch, I'm going to rearrange this a little bit, okay? So I got 6x to the 8th power minus 7, okay, to the 1/2 power. And watch if I put this, x to the 7th power and the dx together. These are all multiplied together, so I can rearrange them however I want. But this will be how I'll get it. Because look, this part right here will be the u, and this part will be the du, because I chose it this way. Because the derivative of this is sort of sitting over there in this other part of the problem, that will make the u substitution work. Now you might say, well, there's not 48. Sure, you can put u, you can let that be 6x to the x minus 7. If you want to, you could do that. But this part, you got to substitute this part too, right? You have to substitute the original variable completely away. Substitution must completely eliminate the original variable. You changed the problem from being in terms of x totally to being in terms of u totally. So I was like, what about the 48? I mean, if this said x to the 7th dx, you could substitute the du, but there's no 48 there. The substitutions have to be exact, okay? But for that, I'd say no problem, because if you want this to fit up there exactly the way it is, and there's this 48, it's out of place. Remember, you can treat this as an equation. You can divide both sides by 48. So I'll use du over 48, okay? Divide both sides by 48, and I'll get x to the 7th power dx. Now, both of these fit up there, okay? Both of these have a place to put. Substitution. We substitute what we see for something different. That makes it simpler, all right? Okay, so yeah, I mean, I guess technically it'll be du over 48, but I substitute everything away, and that's the objective with substitution. So if I, in this step right here, see this step right here, if I apply these substitutions exactly the way you see them in here, then this simple basic rule will become applicable, and that's what we want. So look, I'm going to get u to the 1/2 power, all right? And for this part, I'll get du over 48. What about that 48? What's that over 48? That's a factor of 1 over 48. It's a constant. So I can factor it out of the integral and worry about it later. So I get u to the 1/2 du. So this is what I wanted, okay? That's what I wanted. I wanted to come up with a way to substitute everything that was there, you know, that made it so simple that my basic rule applied. And it's like, okay, I did that. What you're looking at right there is success with that on my part. So let's see. Okay, so the rule is applicable at this point. Here's what we do. We'll just carry the 1 over 48 along. The rule says that we add 1 to the power, so we're going to get 3 over 2. See, if I add 1 to 1/2, I'll get 3 over 2. And then I divide by the same thing that I get, which is 3 over 2. And then I add plus c. Okay, all right. And then like I need to clean up the numbers a little bit. So let's see. I've got this 1 over 48 that's just sitting there. When I divide by 3 over 2, that's the same thing as multiplying by 2 over 3. So I'm looking at 1 over 48 times 2 over 3. And then I got my u to the 3 over 2 power plus c. Okay, let's clean it up a little bit more. So let's see. I could reduce this a little bit. Let's see. 2 goes into 48 24 times. But then if I have 24 times 3, that's 72. So let's write 1 over 72 u to the 3 over 2 power plus c. And then we got it all cleaned up at that point. Do you remember the last step? I have my answer. This is my answer right there. I use the rule to evaluate this indefinite integral. Okay, but it makes sense to give your answer in terms of the variable you started with. The purpose of introducing the u is just to turn something complicated into something so simple that our rule applies to it. So we're done with that. And we want to give our answer in terms of the variable we started with. Okay, so in place of the u, by way of this substitution that is in play in this problem, all throughout the problem, I'll say u is the same thing as 6 times x to the 8th minus 7. All right, so here goes. Final answer, 1 over 72. Okay, what was that? 6x to the 8th minus 7. So 6, whoops. 6x to the 8th minus 7 power 3 over 2 plus c. Okay, and then we're done. That's our answer. All right, now I will make another video with some more problems, but for now, I want you to look back and forth between my guidelines, okay, and the way that I put them into place. All right, when I work the problem. Eventually, I think, like a lot of things in math, it gets to be where with practice, you don't even think about the steps that much. All right, I think if you practice this enough, then you'll have no need to overthink it, even if your tendency is to overthink it initially. You know, you look at your problem from experience, you'll probably know the best choice for you. You calculate the u and the du. You'll see that there's a place for everything. You put everything in its place. You apply some basic rule, and you put the original variable back in. And then that generally will be the whole process.